All right, everybody. Nice to see you all. Thanks very much for braving the weather today. I think I was just saying to Will, if it wasn't raining, this place would probably be full, standing room only. Okay, so we've got a treat today at Science of SLAC. This is Will East from KIPAC, who's going to tell us a bit about some of the theoretical work that goes on here at SLAC about gravitational waves, which I'm sure you're all excited about following the discovery last month. So Will is doing his first postdoc here with us at SLAC. He did his PhD at Princeton, and then when he had the chance to come and work with Roger Blanford and Tom Abel, he was excited about that, and also the chance to use the computing facilities here at SLAC as well. So we're lucky to catch Will. He's actually off in the autumn to become one of the Director's Fellows at the Perimeter Institute. So this is his almost his last hurrah, and a good job too. Okay, so Will, if we can make this work again. All right. Okay, thanks a lot.
So thank you very much for this opportunity to tell you about gravitational waves and what all the buzz has been about lately, as well as a little bit about my own research trying to understand gravitational wave sources with the aid of computer simulations and how that's related. So 2 months ago on February 11th, there was a big announcement. Maybe like me, you woke up early to watch the press conference given by the National Science Foundation, or maybe you heard about this on the radio or saw it on the front page of the news. So this big announcement was that LIGO, the Laser Interferometer Gravitational Wave Observatory, had, for the first time ever, directly detected gravitational waves. So what we learned is that a couple months prior, on September 14th, almost as soon as LIGO had switched on its instrument at its advanced sensitivity, they had detected something which my colleagues have taken to referring to as the event. So what this actually was that something that occurred 1.3 billion years ago, where two black holes, each having a mass about 30 times that of our sun, spiraled towards each other and merged, creating a bigger black hole. And this created ripples in the fabric of spacetime, gravitational waves that we detected here on Earth. And what we learned at this press conference was that these little wiggles here detected at the LIGO instrument in Hanford, Washington, and Livingston, Louisiana, actually told this story. And furthermore, we learned that this whole story that I just said about black holes, how they exist, what happens when they in-spiral towards each other and merge, and how they produce gravitational waves, was actually predicted by Einstein almost exactly 100 years ago. So not only was this, sort of a stunning verification of Einstein's theory, but it was a very fitting centennial celebration. So, this all sounds tremendously exciting, but also leads to a number of questions. What exactly are these gravitational waves? And how are they created? What kinds of astrophysical sources actually give rise to them? And how do we actually detect them here on Earth? And when we do detect them, what can we learn? What can they teach us about the universe around us? So in this talk, I'm going to try to address these questions. So in order to understand what a gravitational wave is, it'll help to go back 100 years ago to Einstein's theory of general relativity. So the tremendously revolutionary idea that Einstein had was that gravity is actually not a force like other forces. It's in fact the geometry of space and time. So what Einstein taught us is that actually massive objects warp space-time. And because space-time is the arena where everything takes place, other objects have to travel through this warped space-time. And Einstein wrote down these equations that tell us exactly how much a given object will curve space-time and how other objects will move through this deformed space-time. So to make this a little more clear, it's helpful to think of an analogy with another type of material that can be deformed or warped, to think of space-time as sort of a rubber sheet. So we know that the Earth goes around the sun because of the sun's gravitational pull. But in this analogy, we can think of the sun as sort of a giant bowling ball that sits on the rubber sheet that is space-time deforming it. And so that's the reason that the Earth doesn't move in a straight line, but moves in this ellipse around the sun with a period of a year that we all know and love. And so you might say, we have a perfectly good description of why the Earth goes around the sun that Newton taught us. And so how is this idea of warped space-time actually different from Newton's theory and not just sort of a more complicated way of describing gravity? So in order to actually understand the essential features of Einstein's theory of gravity and how they differ from Newton's, help to go back even earlier to the 1600s. So Newton's concept of gravity is that gravity is a force. For two objects, the gravitational force between them is just proportional to each of their masses, and it's inversely proportional to the square of the distance between them. And you'll notice that this description of gravity doesn't impose any speed limit. If I take one of the objects and move it a little bit, the gravitational force will instantly adjust. And of course, this theory that Newton came up with was very successful, and it allowed Newton to describe the orbits of all the planets around the sun, as well as why when you take an object on Earth and drop it, it falls to the ground. However, about 100 years ago, Einstein came up with his theory of gravity, in which he told us that gravity is not a force, it's actually the curvature of space-time. And furthermore, he told us that gravity does have a speed limit, that it moves at the speed of light. And in fact, this was sort of one of the essential features that led Einstein to come up with this theory. That's because in his special theory of relativity, he had already declared that essentially nothing can move faster than the speed of light. So he needed to come up with a theory of gravity that obeyed the speed limit. And in fact, as we'll see, the fact that gravity propagates at this finite speed is sort of essential to it having waves. And Einstein's theory gives small corrections to the orbits of planets in our solar system. Most famously, a correction to the orbit of Mercury. And by measuring these, we gain confidence that Einstein's theory was a more correct theory of gravity. But in the solar system, these effects are small, and they require very precise measurements to actually see. So in my talk, I want to talk about a different regime where gravity is strong. And by that I mean when Newton's theory of gravity completely breaks down and has to be replaced by Einstein's theory of gravity as the geometry of space-time. So this occurs when objects are moving near the speed of light and when objects are compact. So let me tell you what I mean by compact. So the way to tell whether an object is compact is to stand on its surface and try to launch yourself with a rocket or a cannon or something such that you can escape that planet or star and escape its gravitational pull and go out without falling back. And you figure out how large a velocity you need to launch yourself in order to escape that star or planet's gravitational pull. And we call that just the escape velocity. So here, of course, we're ignoring the atmosphere or anything that's not gravity. So here on Earth, the escape velocity is 11 kilometers per second. And that may seem pretty fast, but the number to compare it to is actually the speed of light, which is 300,000 kilometers per second. So when I say a compact object, what I mean is something whose escape velocity is comparable to the speed of light. So since we have decided the Earth is not a compact object, let's look at some stars. So the most compact object in our solar system is actually the sun. And that might seem surprising since the sun is the largest object in our solar system, but it's also the most massive. So if you were able to stand on the surface of the sun without being burned, you would need to launch yourself at a velocity of 600 kilometers per second in order to escape the sun's gravitational pull. So it's getting larger, but it's still not close to the speed of light. So let's consider an even more exotic type of star called a white dwarf. So white dwarfs have about the same mass as our own sun, but they're much smaller. They're about the size of the Earth. So the radius is about 1/100th of the sun's. And this means that their escape velocity is about 10 times larger. It's 6,000 kilometers per second. So we're getting closer, but we're still not near the speed of light. And in order to get there, we need to consider an even more exotic type of star called a neutron star. So neutron stars, again, have a mass about that of the sun's. However, they're tiny. They're about 10 kilometers in radius, about the size of Manhattan. And for a neutron star, the escape velocity is about half the speed of light. So a neutron star is a compact object. And as I'll talk about later, they play an important role in producing gravitational waves. But again, just to emphasize, all these stars have about the same mass. So if you're far away from them, you feel the same gravitational pull. But it's just that they get smaller and smaller as we go to the right. And so therefore, they're more and more compact. And when you're close to them, you can feel a stronger gravity. So if we take this to its logical conclusion, we arrive at a black hole. So black holes occur, for example, when stars collapse, and nothing can overcome the gravitational pull, and they just collapse and get smaller and smaller. So black holes don't actually have surfaces that you can stand on, but we just sort of can define the boundary of where a black hole is by the region where the escape velocity becomes equal to that of the speed of light. So that means that inside a black hole, space-time is so strongly curved that nothing, not even light, can escape. For example, if we had a black hole with a mass equal to that of the sun, its radius would be about 3 kilometers. Now, typically we think of black holes as being slightly larger, but their size just scales in proportion to their mass. So for example, for a black hole with a mass 30 times that of the sun, like those involved in the LIGO event, those would have a radius about 90 kilometers. Or if we have a black hole whose mass is about 4 million times the mass of the sun, like we think resides in the center of our own galaxy, that would have a radius of about 12 million kilometers. So far I've just told you about these isolated compact objects that are just sitting there not doing anything interesting, like emitting gravitational waves. So when does gravity actually become dynamic? So that happens when you have objects that are moving near the speed of light. So I'm going to show you here a simulation of 2 black holes merging, just like in the LIGO event. This is an animation by the SSX group. So you can see the 2 black holes going round and round. And each time they switch places, you get this ripple, which is actually the gravitational wave. And you can see they get closer and closer and sending out more and more ripples. And then finally they merge. And then they create these high frequency gravitational waves, which I want you to remember because we'll talk more about those later. So in order to understand gravitational waves a little better, it'll help to go back to a more familiar type of waves that we're all very familiar with, electromagnetic waves, or light. So electromagnetic waves, of course, come in many frequencies, from low-frequency radio waves, which allow us to talk on our cell phones, to visible light, which allows you to see the slide, or for me to use this laser pointer, to higher frequency electromagnetic waves like X-rays or gamma rays. And so all these types of electromagnetic waves all travel at the same speed, which we conveniently just call the speed of light, or 300 kilometers per second. Furthermore, electromagnetic waves all carry energy. That's, for example, why the sun's rays can keep us warm. And if I have a source of light then that goes out in all directions, then the amplitude of those electromagnetic waves will decrease in proportion to the distance you are from them. That's why distant sources of light appear dim to us. And so electromagnetic waves are created when we accelerate charged particles, like the electrons in your cell phone, or as I'm sure many people here at SLAC are familiar with, like at the SSRL or LCLS, where you accelerate electrons at very high energies to create these X-rays. So gravitational waves are actually very similar to electromagnetic waves. So gravitational waves also come in different frequencies. For example, when you have two compact objects orbiting, like in the black hole example we just looked at, then the frequency of the gravitational waves is just in proportion to the orbital frequency, how fast those objects are going around. Gravitational waves also travel at the speed of light. And they also carry energy. That's why the black holes were getting closer and closer to each other, because they were losing orbital energy that was being carried off by these gravitational waves, until finally they had none left and they merged. And also, gravitational waves, their amplitude goes down in proportion to how far away you are from them. That's why it's very hard to detect gravitational waves from very distant sources. In contrast to electromagnetic waves, which are created when you accelerate charged objects, gravitational waves are created when you accelerate massive objects. Now you may think, everything has mass, so it'd be very easy to create gravitational waves. We should be creating them all the time. However, if you want to continue our analogy of thinking of space-time as a rubber sheet, it turns out that it's a very, very stiff rubber sheet. So you need extremely violent events, like two black holes smashing into each other, just to shake space-time a little bit. So what does it mean for gravitational waves to actually be ripples in space-time? So this little animation here shows what would happen if a gravitational wave passes through the slide in that direction. So what happens is that you get a stretching in one direction and a squeezing in another direction, and this alternates as the valleys and peaks of the gravitational wave pass through. And gravitational waves actually, just like light, have two polarizations. So I showed you one polarization, and the other one would just be would be this, but rotated by 45 degrees, so that you're squeezing and stretching the opposite corners like that. By the way, if you go to the SLAC website to download this logo and make this animation, it actually tells you that you're not allowed to distort the SLAC logos. But I want to emphasize here that in this depiction, it's not just the object that's being distorted. It's actually space-time itself. It's the physical distances between two freely floating points that's changing. So hopefully that's okay until they update their website to say that you're not allowed to embed the SLAC logos in distorted space-time. So how do we actually detect these stretching and squeezings of space-time? So here's a picture of one of the LIGO observatories, the one in Livingston, Louisiana. And there's another one in Hanford, Washington. And you can see that it has this giant L-shaped configuration where each of the arms are 4 kilometers long. And I should also mention that there's similar observatories, one in Germany and Italy, and one that's in the process of coming online now in Japan. And so, gravitational wave observatories are really starting to take off. So the reason for this L-shaped configuration is that LIGO is actually a giant laser interferometer. So what does that mean? You have a laser source here that sends a laser beam that's split into the 2 4-kilometer arms, where it bounces back many, many times, and then comes back and is recombined here at the beam splitter, where it's detected by a photodetector. And so, if the arms are exactly the same length, then the laser beams will add up in the same way. However, when a gravitational wave comes through, as demonstrated by this nice animation from the LIGO group, and stretches one direction and squeezes another, then that actually will change the way that the laser recombines back here. And so instead of adding up together, those tend to cancel out somewhat. And then by detecting the way that these two different laser beams interfere with each other, that's how you make a measurement. So this actually seems like a fairly straightforward concept. So why does LIGO have to be so big and so complicated? So actually this is a very simplified diagram. Actually, these test masses are custom fabricated silicon, made out of custom fabricated silica, and they're suspended on pendulums and seismically isolated from the ground. And all these tubes are vacuum sealed. And the reason for all of this is that actually the changes in length that LIGO is detecting are just mind-bogglingly small. So if you take a look at this plot up here, this shows how sensitive LIGO is when it detected the binary black hole merger. And so I just want you to look at the numbers here on the y-axis. So this is saying the strain, the differential changes in length that LIGO is sensitive to are on the order of 10 to the minus 21. Just to give you an idea how small that is. So Alpha Centauri has been in the news lately. That's the closest star system to our own planet. It's about 4 light years away. And this Russian billionaire and Stephen Hawking have this crazy idea to send these robots at near the speed of light there in something like 20 years. Well, LIGO, the differential changes in length that it's sensitive to are equivalent to measuring the distance to Alpha Centauri to the width of a human hair. So it sounds even more crazy. And it really is a marvel of engineering that this works. So what kind of things will LIGO actually see? So the primary sources that is really built to go after are the mergers of compact objects. So you recall that I told you that a compact object is a black hole or a neutron star. So far, it's seen one event that they've told us about, the merger of 2 black holes. But you can also think about 2 neutron stars merging or a black hole and a neutron star merging. And each of these events will have its own special characteristics and very interesting dynamics. And we'll talk about that. Some other possibilities that are maybe a little more rare or speculative include things like stars collapsing and going supernovae, or for example, a background of gravitational waves from the early universe. And maybe even more exciting than that, this is really entirely new way of looking at the universe. Some people say this is sort of we're beginning to hear the sound of the universe instead of just looking at it. And so there's really the possibility for surprises, things that we didn't even expect to see. So how do we actually predict what kind of gravitational waves will come from a given source? Or as hopefully we'll be doing more of in the future, given a particular detection, how do we actually know what created it? So in order to determine what a gravitational wave signal should look like, you need to solve Einstein's equations that describe orbiting strongly gravitating systems. So it's very easy to just write down a solution that describes one black hole or one star. But you'll remember that I told you only get gravitational waves when things are very dynamic. And so we have various approximation schemes that allow us to describe what happens when things are orbiting not that close to the speed of light or spacetime isn't that strongly curved. But all these approximation schemes break down, for example, in the last stages when you have 2 black holes merging, like in the LIGO event. So actually, until about 10 years ago, we didn't have a complete description of what happens in that case and what exactly the gravitational waves should look like. And it turned out that the solution to finding out was to actually put Einstein's equations on supercomputers. And that's sort of essential to understanding and predicting these sources. So that's the kind of thing that I'm involved in. So here's a picture of one of the supercomputers here at SLAC. Some of the simulations that I'll show you were actually run on this. You can see our own director, Kai Pector, Tom Abel, making a little cameo there. So the question is, why do we have to use these big supercomputers to solve Einstein's equations? So first of all, the equations that Einstein gave us are a complex coupled system of nonlinear partial differential equations. So that just means that if you have a description of one black hole, you can't just add the description of another black hole on top of that to understand what happens when you have two black holes orbiting each other. They interact in a complicated way. Another reason is that when you're studying these orbiting and merging systems, there's a range of length scales that need to be resolved, that going all the way from the size of the individual objects to slightly larger the orbital scale, the length of their orbit. And then you have to go even farther away and resolve the region where you can detect gravitational waves far away from the system. And finally, we don't want to just study gravity. When we study things like neutron stars merging, for example, we want to add the effect. We want to add lots of other physics. We want to understand how the star's material flows. We want to understand the effect of magnetic fields on this strongly curved spacetime, radiation, and so on. And so that's the reason we really need to use these big computers to understand what goes on in these gravitational wave sources. So just to give you a little bit of a flavor for these different kinds of compact object mergers, I'll show you a couple of simulations from each example. But first of all, I just want to note that up until the LIGO detection, we'd actually never seen two black holes orbiting each other, even using ordinary telescopes, let alone two black holes merging. So that's one of the reasons this detection is really so spectacular. And as of now, we still have never seen a black hole and a neutron star orbiting each other, let alone merging. And using ordinary telescopes, we have seen some examples of two neutron stars orbiting each other, but they're very large distances, and they'll take millions and millions of years for them to actually merge. So this is really a new frontier, and this is another reason that sort of doing this theoretical work and this computational work is essential to understanding these systems. So first of all, let's talk about black holes merging with black holes. So this is, again, the September 14th LIGO event. But instead of showing you the noisy signal that was actually detected, I'm showing you a reconstruction of the signal using a computer simulation. So you can see that as the black holes spiral around each other, you get this almost like a sine wave. And then as they get closer and closer to each other and orbit faster and faster, the frequency and the amplitude of the gravitational wave increases. And then finally, these two things merge, creating this distorted black hole, which then undergoes something called a ring down. That's these high-frequency gravitational waves. So if you recall you can watch the simulation one more time. So this time I want you to pay attention to the ring down that happens right at the point that the two black holes merge, creating this distorted black hole. So you can see these high-frequency gravitational waves that are coming from the ring down. And so it's actually this earlier part of the gravitational wave signal would be similar if you had, for example, two neutron stars orbiting each other. However, this final part right here is really, sort of the characteristic smoking gun of a black hole. And by measuring sort of the frequency of this signal, you can tell exactly how big the final black hole was that formed. And in fact, the LIGO collaboration used this to tell that the black hole that formed actually was 3 solar masses smaller than the sum of the mass of the two original black holes. And you may ask, where did that extra mass go into? It went into the gravitational waves. So this is actually an extremely energetic event. At its peak power, this gravitational wave was actually outshining all the stars in the universe. So now let me tell you what exactly I mean by a black hole ringing. So it turns out that black holes are actually kind of like bells. Just like a bell, if you perturb a black hole, if you have a star smashing into it, or if you create a distorted black hole by merging two black holes, the black hole actually ring. It'll vibrate, but instead of emitting sound waves like a bell, it'll emit, as you can guess, gravitational waves until it settles down to its preferred shape. So to illustrate this, I'm going to show you a computer simulation here where the way that we're going to perturb the black hole is actually by sending in gravitational waves that'll be shown in blue. You can think of this as sort of analogous to blowing on a wine glass to make it vibrate. So it's something that's very hard to arrange for astrophysically, but is easy to arrange for in a computer simulation, and it has the same effect. So you see send in some gravitational waves to perturb this black hole, and then it starts ringing and emits these outgoing gravitational waves in red. And encoded in the frequency of these gravitational waves is exactly the mass of the black hole and how fast it's spinning. So to make things even more interesting, let's throw matter into the mix and talk about mergers of neutron stars. So neutron stars are already suspected to be responsible for a whole host of electromagnetic signals that we see with ordinary telescopes. That's because they're these very compact objects that can be rapidly spinning, that have very strong magnetic fields. So one of the big things that people are excited about is the possibility of doing multi-messenger astronomy. That's where we would hopefully simultaneously detect a merger using gravitational waves on the one hand, and also using electromagnetic waves on the other hand. Using electromagnetic waves from radio all the way to the highest energy gamma rays. And there's a possibility of doing this, for example, with instruments that people are very familiar with here at SLAC, like LSST or Fermi. So for example, when Fermi or other gamma ray instruments look out into the sky, they periodically see these short, very energetic bursts of gamma rays that last about a second or less. And so one of these sort of outstanding puzzles in astrophysics is what causes these short gamma ray bursts. And actually the leading explanation is that they come from two neutron stars merging, or a black hole and a neutron star merging. But really the smoking gun that would tell us that this hypothesis is correct would be to detect one of these events simultaneously using gravitational waves and detect the short gamma ray burst. And in fact, one of the things that the simulations can tell us is whether or not these mergers actually give rise to the right conditions to create a short gamma ray burst. And it actually turns out it depends a lot on the details of the merger. Another thing that's exciting about neutron stars is that they might teach us about nuclear physics. So that might seem a little bit surprising that we can use gravitational waves to learn about nuclear physics. But you recall that I told you a neutron star is what happens when you take all the mass of the sun and compact it down to a 10-kilometer radius ball, like the size of Manhattan. So as you can imagine, these neutron stars are incredibly dense. In ordinary units, their densities exceed something like 10 to the 15 grams per centimeter cubed. Or in more whimsical units, like you might find in some cosmic cookbook, if you took a teaspoon of neutron star material, that would actually weigh 1 billion tons. And so, these are densities that we don't have any access to here on Earth. But it turns out that the properties of nuclear material at these densities actually determines For example, how big a neutron star of a given mass will be, or what the maximum mass a neutron star can be before it collapses to a black hole is. So there's a hope that we can learn about nuclear physics in this regime by studying the mergers of neutron stars. So let's talk about black holes merging with neutron stars. So here's a simulation of a black hole in the top, and then you'll see the neutron star wander onto the frame in a second. So in this case, the neutron star is on the larger side, and when it gets near the black hole, it gets pulled apart in something called tidal disruption. And then some of the material falls into the black hole, and then it comes back and is completely pulled apart. And so some of this material is flung out, and some of it surrounds the black hole. So the tidal in tidal disruption actually refers to the fact that when the when the neutron star gets close to the black hole, one side of the neutron star is closer to the black hole than the other, and so it feels a stronger gravitational pull. And this is in the same way that one side of the Earth feels a stronger gravitational pull from the moon than the other, and this is what gives us ocean tides. And so whether or not you have tidal disruption will tell you how much material you have left over after you merge, and it also affects the gravitational wave signal from these events. So on the bottom, I'm showing you the gravitational wave signal from the end of this example that we just looked at. And the gravitational wave signal is actually kind of wimpy because the star got pulled apart. For smaller neutron stars that collide with the black hole without being torn apart, then you get stronger gravitational waves, like on this bottom case here, that look more like the two black holes merging.
Is that a 1 solar mass black hole?
This one is like a 5 or 6 solar mass black hole. So let's talk about neutron stars merging with neutron stars. So just to illustrate two possible outcomes, I'm going to show you these two examples. So in the first case, the neutron stars collide and immediately collapse to form a black hole. In the second case, that's only slightly different. When the two neutron stars merge, they actually create this larger neutron star. We call it a hypermassive neutron star. And some of the material gets flung out, and some is left in this disk around the star. And actually, this oscillating hypermassive neutron star can last for a while. And which of these outcomes occurs actually depends on a number of things: how big the neutron stars are, whether they're spinning or not, and the unknown behavior of nuclear physics at these very high densities. And as you can imagine, and I'll show you in a second, which of these outcomes occurs actually also affects the gravitational waves you get from these different merger events. So before I show you the gravitational waves, let's take a zoomed in view of the end of the two neutron stars merging. So in this case, you see the stars merge, and you get these complicated and very turbulent behavior. Some of the material is flung out. But this oscillating star actually begins to develop this wobble. And we actually call this wobble a one-arm mode. You can see that it persists for many, many oscillations. And so, as you might imagine, this wobbling of the star is actually imprinted on the gravitational waves that come from it. So I'll show you those. So here we're looking at the gravitational waves from that same event. And first of all, you can notice that unlike the black hole case, where after the two black holes merged, you have the signal that died down after a few oscillations, here you have these gravitational waves that can persist for many, many oscillations, perhaps as long as a second or two. And second, you can notice that these oscillations are occurring at very high frequencies, 1,000 or more times a second. So this actually means that they'll be more difficult for LIGO to detect because it's less sensitive to these higher frequencies. So we'll need to get lucky with a closer event to actually see these. But there's potentially a lot of information encoded in all these oscillations about the exact properties of the star and the violent merger event that created it. So finally, I just want to mention how these neutron star mergers are not just figuratively, but literally gold. So sort of one of the outstanding problems in astrophysics is to answer where all the heavy elements came from, including shiny metals that we all know and love, like gold and platinum. So we actually don't have the conditions on Earth to create those heavy elements. So sort of the original idea was that stars collapsing and then going supernova were what created these heavy elements and sort of spewed them out into the universe. However, it's actually looking more and more likely that a major source of these heavy elements, like gold, could actually be two neutron stars merging, like an example we just saw. And some of the material, this very dense neutron star material, gets flung out and unbound from the system, where it can go out into the wider universe and go into creating planets and things like that. And so that's something to think about the next time you put on a gold ring, for example, that there's a good chance that gold actually came from two incredibly dense stars merging together at the speed of light and creating ripples in space-time. So that sort of brings me to the conclusion of my talk. So it's of course very exciting to have this first detection of gravitational waves, but really this is just the first of hopefully many more to come. We've really begun the age of gravitational wave astronomy, and we have this completely new way of looking out into the universe. So some things to listen for that might hopefully happen in the near future would be, not just more detections of black holes merging together, but the first detection of a black hole merging with a neutron star, and the first detection of two neutron stars merging together. And whether or not this confirms or refutes this idea that they're actually what caused these short gamma ray bursts that we've been seeing. And even more exciting than this is the possibility that using gravitational waves, we see things that we just didn't have the imagination to think up of before. And that sends us back to the chalkboard or back to our computer simulations to try to figure out where they came from. And that's the really exciting thing about doing science. So thank you.
All right, excellent. Thanks very much, Will. So I think we have time for some questions. Probably have lots about these things. Kevin.
I'm just curious about ordering of things. So this ringing of two black holes when they merge, did you see it and then try to figure out what it was, or know what it was? Or did you know in advance what you should see if two black holes merged, and then when you saw it, you said, aha, we know what that is? For example, in these unknown unknowns, you're going to see stuff and have no clue what it is and figure it out. I'm just curious about this particular event. Did you know in advance?
Yeah, so definitely the mergers of two black holes was one of the main sources that LIGO was going after, and they had all these templates and analysis, in their already in place to look for these kinds of things.
I'm sorry, I should have remembered. We should wait for the microphone to get to you before.
Yeah, sorry, that's my fault. There we go, thank you.
Thank you. I have two related questions. The first one is what you said at the beginning, that the event happened 1.3 billion years ago. Mm-hmm. Now, which part of the measurement told you that? That's the first question. How do you know that it was 1.3 billion years ago?
Yeah, so that's basically, it's that's how far away it is in light years, basically. And so by basically measuring the redshift and sort of how strong the gravitational wave is, that's how we determined how far away it came from.
The redshift?
Yeah, so it corresponds to a redshift about 0.1.
Okay. The second question is maybe naive, but you said that special relativity shows that, or is based on the idea that no material object can move faster than light. Okay. But that doesn't necessarily mean, although you seem to imply it, that gravitational waves are moving at the velocity of light.
Right. So I mean, that was sort of the fact that you have gravitational waves and that they move at the speed of light is a prediction of general relativity, not special relativity. But what special relativity tells us is that, in some sense, if you have some signal that you can send faster than the speed of light, then according to some other observer, they can mix up, whether the order in which you sent the signal in which you received it, so that another observer would see the signal received before it was sent. So if you had gravitational waves that you could send faster than the speed of light, then you could basically mess up causality.
Chap in the middle here. Very good. You can pass that right. Thank you.
Hi. So you showed us some characteristic signals from all sorts of mergers. I was curious, are there any characteristic signals that come from supernovae that you could talk about?
Yeah, so that's something that's very much an active field of research. So originally people thought that supernovae were going to be one of the major sources, but it actually turns out that if you have something that's completely spherical, even if it's collapsing, then you don't get any gravitational waves. And so it actually turns out that supernovae, sort of the collapse, seems to be more spherical than we expect. But actually understanding all the details of what you get out of a supernova is something that people are still looking at. But it would be something like these higher frequency oscillations that you saw in the hypermassive neutron star.
It's a great talk. One particular question about the September 14 event is you have a simulation of the velocities, and it seems that the slower black hole is catching up speed, is getting faster, and the faster one is becoming slow. But at some point they cross over, and the slower is then faster than the...
Sorry, that might have been a little confusing, but actually one of those, there was two different axes. So one of them showed velocity, and one of them showed distance. So this is just the relative velocity between the two black holes, and then this one is the distance. So they're getting closer together and going faster.
Where is the redshift there?
Huh?
Where do you see the redshift?
Well, so this is what was actually measured in the detector, but sort of by sort of seeing how weak the signal was, that sort of tells you how far away it is, right?
So it's not that you measured the redshift; it's that you can measure the distance from modeling the signal. Is that right?
Yeah.
So they're like standard candles. The model tells you how big the gravitational wave signal should be, and so how faint you hear it to be.
For a given mass, but I mean, you can have black holes of different masses, so they're not actually standard in that sense, but yeah.
So could you please go back to your slide with the simulation of the incident gravitational wave and reflected gravitational wave from black hole? Yeah, like this one. So you say incoming wave is blue. So why after some time, when the incoming wave actually absorbed by the black hole, you still can see the blue color? I mean, if it's like incident wave, and then you should see after some time you should only see like red.
Yeah. So I mean, you should really pay attention to.
Can you run it again so we see? Can you run it again? I will show.
Yeah. But so I just want to say that though, I mean, you can't really define the waves except far away from the black hole. So I mean, this is just sort of a visualization, but this part here actually doesn't correspond to gravitational waves. Yeah, it's just an artifact of the visualization.
Oh, yeah.
So you said that LIGO can what to look for. Now, does LIGO have been tuned into looking at some specific kind of signal, a little bit like a particle detector for HEP, or does LIGO just look for all the different kind of sources at the same time?
Yeah, they actually have like a number of detection pipelines. And some of them are looking for very specific signals from compact object mergers or something like that using templates. And some are looking for more unmodeled things like bursts or something like that. They're just looking for coincident power in the two detectors and so on. So there's actually a number of different detection pipelines, going from using all the theoretical information we have for what we think and then trying to get away from that and just look for a signal.
Hi. I wonder if, this is a trivial question really, but I wonder if it worries anybody that the way you are using to invoke in the minds of us, the simple public, what a geometrical distortion, how a geometrical distortion actually causes the things we call gravity, is this distorted rubber sheet, and you rely on our perception of how things will move under gravity in a distorted rubber sheet in order to get the effect in our minds. So isn't it rather circular that the circling around the distortion is due to gravity, not really due to the distortion of the geometry of the rubber sheet?
Yeah, so I guess it's an imperfect analogy in that way, but maybe you could think of, instead of a bowling ball, you could charge the ball and then pull with electromagnetic forces or something. But
the geometrical distortions that will produce the effects of gravity, I don't know, but okay.
I had a question about the simulation where the neutron star and the black hole were circling. And it seemed at the beginning, I'm wondering if this is an artifact, that there was actually a jet emerging from the black hole on the opposite side of the neutron star for just a moment as it began to approach.
Yeah, that was just an artifact of the simulation. It's not something you really expect.
Really nice talk. Really nice talk. So now that we know that LIGO has enough sensitivity to see merger events like the one that was detected, what is the estimate of the rate at which we will observe similar events in the future with the current sensitivity?
Yeah, so that's a very good question. So, before LIGO, we had never seen any binary black holes, so all the estimates were sort of theoretical. Now we've seen one, so that helps a lot, but there's still a lot of uncertainty. But I should also mention that LIGO is not quite actually at its design sensitivity yet. They're still in the process of putting in all the upgrades. And so once it reaches its design sensitivity, it'll be about 3 times more sensitive, which means you'll be able to see 27 times more volume of events. So I think it's still somewhat uncertain how many of these binary black hole mergers we're going to see. But unless we're very lucky, I mean, this is something that should happen regularly, and we'll see a lot of them.
What are some of the difficulties that you face with doing these simulations? Like
Sorry,
key assumptions that you have to make. You don't have all the data, right?
Yeah, so I mean, these simulations just sort of explore various scenarios, and then we hope that we can detect something that's similar to them. But yeah, we don't, like I said, we don't know exactly what sort of ratios of mass to expect in these different systems, or exactly what the behavior of nuclear physics is at these very high densities that determines the exact size of a given neutron star. So we just sort of put in different assumptions and see how that affects the outcome. And then hopefully when we observe things, we can sort of back out which one of those assumptions were right.
He answered the question. Very good. So the question I have is how you verify these numerical codes. So what's the strategy? Are there multiple ways to check the code? What's the strategy for getting some sense that these codes are doing what you think they're doing?
Yeah, so one of the things you can test is run the same code, the same simulation at multiple resolutions, make sure you're resolving everything. The Einstein equations actually have some nice properties that there's sort of some redundancies built in. So if you solve some subset of the equations, then other ones will automatically be satisfied. So you can always check that those other ones are automatically satisfied. And also, I mean, there's a number of groups out there doing similar types of simulations, so people compare the results against each other.
It's presumably more difficult when you get into the material of neutron stars, et cetera, many more assumptions.
Yeah. Things are always messier with matter.
Yeah, a quick follow-up question to the matter. Is it actually understood what happens to this neutron star matter when it is flung out of the neutron star by the merger? What happens to that?
Yeah, so I mean, we have some understanding of that. So, I mean, the idea is that you actually undergo this process called the R process, where the neutron stars get captured onto a nucleus, and you build up these heavy elements. So you can make sort of predictions of what the abundance of different elements should look like for this material and compare it to other things like the material that gets flung out from supernovae or something like that.
Okay, one at the back.
At the time of the gamma ray burst event, there was it was reported that Fermi had seen a weak gamma. I mean, at the time of the gravitational wave event, it was reported that Fermi had seen a gamma ray burst weak, and I think 0.4 seconds after the event.
Right.
Do you have any way of getting gamma ray bursts out of two black holes merging?
Yeah. So that was definitely not something that people expected. There have been a couple of ideas that have been sort of batted around for trying to get a short gamma ray burst out of two black holes merging. None of them are entirely convincing yet. And so there's a good chance that maybe that's just coincidence. But hopefully, as we detect more of these things, if we keep seeing short gamma ray bursts, then maybe we need to go back and think of a better explanation for that.
All right, so if there are no more questions, I think we should thank Will again for an excellent talk.